Hello everyone, welcome to Vyas Edification Kota. In this session, we are going to discuss class 12th, chapter number 5, Magnetism and Matter and NCERT All and Exercise Solutions. Clear? So, in this session, you will find the detailed solution of each and every question, as well as you will find here the detail, or we can say theory behind that question also. Clear? So, definitely this session will be very fruitful to you. So, now we are going to start all the questions. So, let's start. Now, dear student, we are going to discuss question number 5.1, and in this question it is given to you, answer the following questions regarding earth magnetism. Clear? So, in this question different sub questions are given to you. So, in the first slide you can see here we have total 3 questions. Clear? So, now if we talk about part number A, so in part number A it is given to you, a vector needs 3 quantities for its specification. Clear to you? Name the 3 independent quantities conventionally used to specify earth magnetic field. Clear? So, now concentrate on a screen. Now listen carefully. Let's suppose if we want to define earth magnetic field, actually we need 3 essential elements for earth magnetism. Clear? And what are 3 different essential elements we have? Number 1. So, if we are talking about part number A, definitely we can say first vector or first element that we required, this is magnetic declination. Magnetic declination. Magnetic declination. Clear? So, now what is the meaning of magnetic declination? Magnetic declination is an angle, it is made of between geographical meridian and magnetic meridian. Clear? So, now we can say, let's suppose you can assume like this, let's suppose this is earth. Clear? We can say this is geographical north and we can say this is geographical south. Clear? Now, we can say this magnetic meridian is lie approximately having some angle 14.2 degree. Clear? So, we can say this is here we are having magnetic south and we can say this is magnetic north. Clear to you? So, now we can say if we talking about a plane that passes through geographical north and geographical south, and there is one plane that is passes through magnetic south and magnetic north. So, we can say the angle between these 2 planes, it is known as magnetic declination. Clear? So, one of the element that is used here, this is magnetic declination. Clear to everyone? Now we are going to discuss second element, and that is what? That is known as angle of dip. Angle of dip. Clear? Angle of dip, let's suppose if I am represented by del. So, what is the meaning of angle of dip? Actually, this is angle made by resultant magnetic field with horizontal component of magnetic field. Clear? So, this is angle of dip, and definitely we need one more important parameter, that is horizontal component of velocity, horizontal component of earth magnetic field. Horizontal component of earth magnetic field, and we can say that is represented by BH. Clear? So, if we talk about part number A, we need here 3 independent quantity that is used to specify earth magnetic field. Number 1, magnetic declination, second one angle of dip, and third one horizontal component. Clear? Horizontal component of magnetic field. Clear to you? So, this is all about part number A. Clear? Now we are going to discuss part number B. Clear? In part number B, it is given to you the angle of dip at a location in southern India is about 18 degree. Okay. Would you expect a greater or smaller dip angle in Britain? Now, actually all are some theoretical questions. Actually, there is so many theories that is developed for the earth magnetism. Clear? Some is accepted, and this is again a fact base. It is given here. Let's suppose if you are talking about angle of dip at a location in southern India. In southern India we have 18 degree. But if we are talking about Britain, clear? Britain. So, we can say in if we are talking about Britain, Britain is situated near about north, we can say Britain is situated near about magnetic north. Yes or no? And if we are talking about magnetic north, definitely we can say angle of dip will be more as compared to India. Clear? So, it is generally seen that if you are talking about Britain, for Britain we have angle of dip, this is near about 70 degree, clear. Now you can say, sir, how do you know? Actually, let's suppose we have a dip needle and now we are moving at a different location at a different location of a world, clear. So we are actually observing different dip angle, clear. So that's why we are saying if we go for the Britain, at the Britain we are getting angle of dip, this is equal to 70 degree, clear to everyone. So this is all about part number B. Now if I talk about part number C, in part number C it is given to you, if you made a map of magnetic field lines at Melbourne in Australia, would the line seem to go into the ground or come out of a ground, clear. So now if you know the geometrical location of Australia, Australia is actually located in southern hemisphere, clear. So it means we are talking about geometrical south, clear. We can say we have two, that is geometrical north and geometrical south. So Australia is located in geometrical south, clear. But if I am talking about magnet, so magnetic north is situated in we can say in near about Melbourne, clear. So whenever we have magnetic north, and let's suppose we are talking about at a surface, definitely we know from a north pole magnetic field lines will come out, yes or no. So if we are talking about this part number C, magnetic field lines in Melbourne, definitely it will seems to go, it seems to come out of the ground, clear to everyone. Answer is very clear, answer is very clear. What is this? If we are talking about Australia, Australia is situated in southern hemisphere, clear. If you are talking about southern hemisphere, there is magnetic north will lie, clear. Whenever we have magnetic north, definitely field lines will come out from ground. So directly we can see here magnetic field lines come out from ground, clear to you, yes or no, clear. So this is all about part number C, clear. Now if I talk about part number D of this question, in this question it is given to you, in which direction would a compass free to move in the vertical plane point 2 if located right on the geometrical north or south pole, clear. So now listen carefully. If I am talking about Earth, definitely we can say here we have two situations, and this is known as equator, clear, and we can say this is known as pole. Definitely you know we have two types of pole, north pole and the south pole. If I am talking about angle of dip, clear, so you can say at equator you will find the magnetic needle that is parallel to horizontal component of Earth magnetism, clear. It means here we will find angle of dip 0, but as we move from equator to pole, at pole we will find angle of dip that is equal to 90 degree, clear. So you can say if you are either you are talking about north pole or south pole, angle of dip is 90. Whenever we have angle of dip 90, it means we have only vertical component of magnetic field, clear, there is no horizontal component. So it means we can say if we are now talking about geometrical north or south pole, clear, we can locate that needle in any direction, because there is no any external, there is no net magnetic field is acting in horizontal direction, clear. So this is all about part number D, clear, done. Now if I am talking about part number E, in part number E it is given to you the earth field, it is claimed roughly approximately the field due to a dipole of magnetic moment 8 into 10 to the power 22 joule per Tesla, okay, located at its center. Means we can see here one value is given to you, this is magnetic moment value, clear. Magnetic moment we have 8 into 10 to the power 22, this is joule per Tesla, clear. It is also given it is located at its center, fine. Check the order of magnitude of this number in some way, clear. So let's suppose if we calculate here magnetic field at equatorial position, you can calculate in axial position or equatorial. Let's suppose I am calculating with equatorial position, clear. So if we are talking about equatorial position, we know formula is given by mu naught upon 4 pi, this is multiply m upon r cube, clear. Mu naught upon 4 pi, mu naught upon 4 pi equal to what? 10 to the power minus 7, clear, and it is multiplied with small m. Now what is small m? Small m is known as magnetic dipole moment. So we can see this is 8 into 10 to the power 22 divided by, now what is value of r? Now here we will take value of r, that is radius of earth, clear, and we know this is equal to 6.4 into 10 to the power 3, clear, 6400 kilometer. So we can say 6.4 into 10 to the power 3 into, we can say 10 to the power 3 whole square, clear. Yes or no? We know radius 6400 kilometer, we can convert into meter, so we can write like this, clear. Here we have cube, clear. Now if we simplify, we can write like this, 8 multiply, we can say this is 10 to the power 15, clear, and divided by, this is what? 6.4, 6.4, 6.4, 6.4 multiply 6.4 multiply 6.4 multiply, I can say this is 10 to the power 6, so we can write like this, this is 10 to the power 18, clear to you. So from here you can say this is equal to what? 10 to the power 3, clear. 8 upon 6.4, 6.4, 6.4, clear. So you can say this is approximately 216, clear. 216, it means you can say approximately you will get here value, this is 0.3 something, clear. Or you can also write like this, if you calculate you will find here this value 3 into 10 to the power minus 4, clear, and we can say Tesla, clear. You can also write like this, this is equal to near about 0.3 Gauss, clear, yes or no? 0.3 Gauss. Now, so from here you can see, we are getting this value, and this is near about the earth magnetism value, clear. So now we can say that this value that we are assuming, that is perfectly correct, clear to you. Now if we are talking about part number F, in part number F it is given to you in a question, geologists claim that beside the main magnetic north-south poles, there are several local poles on earth surface oriented in different direction. How is such a thing is possible at all, clear. Actually you know, in our earth we are assuming we have two poles only, north and the south poles, clear, and we are also talking about equatorial position, but you know that it is assumed that we have so many position of a pole, clear. So why this is happening? Actually we can say in our earth we have so many magnetic materials, and these magnetic materials are located at different location, clear. So definitely they are responsible for we can say for small north and the south poles, clear. So definitely we can say here, yes, definitely we have main north and south poles, but apart from that poles we have so many small north south pole also, clear. So this is claimed by geologists, clear to you. So this is all about this question, clear. Now dear student, we are going to discuss question number 5.2, and in this question again we have sub part of this question, clear. So now we are going to start each part one by one. Number 1, in this question it is given, answer the following questions, okay. Part number A, the earth magnetic field varies from point to point in space, okay, fine. Does it also changes with time? If so, what time scale does it change appreciably? Now listen carefully. First of all, if I am talking about earth, let's suppose if I draw here, let's suppose you can assume this is earth, clear. Here we have geographical north, clear. Here we can say this is geographical south, clear. If you let's suppose if you are taking a plane and that plane is actually passing through geographical north and south, we can say that is geographical meridian, clear. But if I am talking about this one plane, this plane, clear. Now we can say here this is, we have magnetic south, or we can say this one is magnetic north. How can we say? Let's suppose if you place a bar magnet, you can assume any bar magnet that is situated at a center of earth like this, clear. Now I am taking here, this is a north pole and we can say this one is south, clear. Now if you draw here magnetic field lines, you can see magnetic field lines that is coming out from this north pole and it is going to the south pole like this, clear, and definitely inside it is moving from south to north pole, clear to you. Similarly, you can draw here magnetic field lines like this, clear. So, we can say magnetic field lines is actually starting from north pole and it is going to the south pole, clear. Now, you can see if we talk about relative strength of magnetic field, definitely we will find relative strength, we will find at this position will be more. Here relative strength of magnetic field it will be more, but if I am talking about these points, if I am talking about these points, let us suppose if I am saying like this, clear. If I am talking about magnetic field at this point, definitely we can say here we are having strength of magnetic field, it will be less compared to this one, clear. So, definitely we can say value of magnetic field it will vary from space to space, but this value also vary with time. Yes, actually magnetic field value also vary with time. Let us suppose if you are considering, let us suppose you are observing this point, clear, and if you are observing value of magnetic field, clear, but it takes hundreds of years, clear, you have to wait for hundreds of years, and after some time, after that time you will find some appreciable change in magnetic field. But if we are talking about just for a few years, let us suppose 10 years, 20 years, 50 years, you will not find any appreciable change in a magnitude of magnetic field at a particular location, clear. So, yes, definitely it is true, value magnitude of magnetic field it varies from space to space, but with time definitely it changes, yes, but it takes hundreds of year time, clear. So, this is all about part number A, clear to everyone? Yes. Now, if I am talking about part number B, so in part number B it is given the earth core is known to contain iron, clear. Generally it is assumed that the earth, on the center of earth we have an iron, clear, and we can consider it as a bar magnet, and that due to that bar magnet we can say there is a magnetic field lines that is to be there for the earth, clear. But it is given in this question, earth core is known to contain iron, fine, yet geologists do not regard this as a source of earth magnetism. Why? Because because we know as we move from the surface of earth, and that is we are going deeper and deeper inside earth, definitely temperature and pressure increases, clear. So, if we are talking about center, so at center we are having a very high temperature, clear, and at that temperature definitely we will find iron in a molten state, yes or no. So, it is assumed that whenever we are talking about iron at a higher temperature and we are getting iron as in a molten state, it means definitely that temperature is above the temperature of a Curie temperature, clear. It means we can say properties of iron is changes when such high temperature is to be there, clear, or we can say its ferromagnetic property changes, clear. It means we can say yes, that is why we can say the geologists do not regarding this as a source of earth magnetism, clear. So, I think this part number B is also given to, is also clear to you, clear. Now if we talk about part number C, in part number C it is given the charge current in the outer conducting region of earth core are thought to be responsible for earth magnetism. Okay. What might be the battery to sustain these currents, clear. Now listen carefully. Now when geologists assume that definitely at a center we have very high temperature, iron is situated in the form of liquid, so we cannot regard iron as a source of magnetic field line at that time, but it is given in this question that charge current in the outer conducting region of the earth core are thought to be responsible for earth magnetism. But geologists actually assume that there is a definitely an current that is actually flowing inside earth, so that we can assume that circular loop as a source of magnetism, clear. Actually such as you can assume it as a, let us suppose you have a wire, in the wire let us suppose a current is flowing, clear. So, definitely whenever we have a wire and we have a current carrying wire and that current carrying wire is in a form of a loop, then at that time you can say definitely we will find magnetic field and definitely we can calculate value of magnetic field also, Clear? So same as geologists assume that definitely here we have a current carrying circular loop, and due to this current carrying circular loop this magnetic field is producing. Clear? So but now we can say if there is a current, then what is the source of that current? So generally it is assumed that radioactivity is one of the source of this type of current carrying loops. Clear? Because we know in our earth we have so many minerals, we have so many natural substances, and definitely there is some radioactive substances also, and these radioactive substances are forming the we can say they are actually forming charge current. Clear? So radioactivity is assumed to be as a source of battery for this current. Clear? Now if I am talking about part number D, in part number D it is given to you the earth may have even reverse the direction of its field several times during history of 4 to 5 billion years. Clear? Now how can geologists know about earth magnetic field in such a distinct past? Now you can say, sir, we have assumed that there is a magnet at the center of earth, and definitely due to this magnet we have magnetic field lines, that is clear to us. But sir, it is geologists assume that this direction of magnetic field lines is reversed after some time. How it is possible? It is possible. Clear? And how can we know for the such distinct past? Actually we know magnetic field, whenever there is some change in the magnetic field lines is to be there, that property is actually stored in a rocks, or we can say or the magnetic materials that we have found on a surface of earth. Clear? If we take that rock into consideration, and if it if we find the properties of that rock, due to that properties we can say that after 4 to 5 million years or billion years, we can say earth actually changes its direction of magnetic field several times. Clear to you? So this is all about part number D. Now if I talk about part number E, in part number E it is given to you the earth field depart from its dipole shape substantially at a large distance greater about 30,000 km. Clear? But what agency may be responsible for this distortion? So definitely we know, if we are talking about magnetic field due to dipole, so definitely we know that earth magnetic field is to be there and its area of expansion is very large. But let's suppose this magnetic field lines is going, that is away from earth, and as it reaches to ionosphere, so in ionosphere definitely there are so many ions is already present there, and these ions are taking their energy from solar system. Clear? Or solar energy. So we can say actually these ions are responsible for distortion of magnetic field due to earth magnetic field. Clear to you? So this is all about part number E. Now if we are talking about part number F, so in part number F it is given interstellar space has an extremely weak magnetic field of order of 10 to the power minus 12 Tesla. Fine. Can such a weak field of any significance consequence? So let's suppose we have any charged particle, and let's suppose that charged particle is actually moving in a uniform magnetic field, and let's suppose I am assuming that uniform magnetic field is perpendicular to that direction of motion. Clear? So at that time I can write here the radius, value of radius, this is given by mv divided by qb. Clear to you? Yes or no? So from here you can say, if we are talking about extremely weak magnetic field, clear, it means we can say this value of B is very less. Clear? At the time you can say this value of R will be more. Clear to you? So when value of R will be more, it means we can say whenever we have extremely weak magnetic field, at the time we will find radius is more. Clear? So let's suppose if we are talking about some particular distance movement, at the time we will not find any appreciable change in a magnetic field. Yes or no? But let's suppose if we are talking about, let's suppose we are in a weak magnetic field. Clear? So definitely we can say radius of curvature is increases. Clear? So just a significance is here. If we are talking about weak magnetic field, radius of curvature is very large. Clear? And you will find that charged particle is moving approximately in a straight line. Clear? So this is all about this question. Clear to everyone? Now student, we are going to discuss question number 5.3, and in this question it is given to you a short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experience a torque of magnitude this much. Okay, what is magnitude of magnetic moment at this magnet? Clear? So let's suppose given situation is like this. Let's suppose here we have a magnet. Let's suppose this is magnet, and let's suppose this one is north and this one is south. We are placing this magnet in a uniform magnetic field. So let's suppose I am saying magnetic field is now in this direction. Let's suppose this is uniform magnetic field. Clear? Now if I am talk about a magnetic moment direction, and I can see this is, let's suppose this is in this direction, that is small m. Clear? And it is also given here this short bar magnet is placed with its axis at 30 degree with a uniform external magnetic field. Clear? It means we can say this angle we have 30 degree, and it is actually experiencing a torque. Why this is experiencing a torque? Actually, now we know whenever we place this magnet in a uniform magnetic field, now force will act here. Clear? So we can say in this direction, definitely we can say magnetic force F equal to mb. This will act in this direction, right direction, and a force will act in an opposite direction. I can say this is also equal to mb. Clear? Now you can say both are both forces are having same magnitude but opposite direction. Clear? So it means we can say net force this is acting on this magnet, that is what? 0. But what about torque? Because these forces are not having same line of action. So definitely we can say here torque will act. Clear? So how can we calculate here torque? So let's suppose if I am taking here, this is the position of center of mass. Clear? I can say here definitely if you find this distance, so force into perpendicular distance, from here you can say this is force into perpendicular distance, and both are having same direction. Yes or no? We can say from this point we can say this is in clockwise direction, this one is also clockwise in direction. So like this you can derive the expression of torque. Clear to you? So from here we can, I am directly writing here formula of torque. Formula of torque, this is given by mb sine of theta. You know very well. Clear? And we can also say it may be written like this also in a vector form. Tau, this is given by m cross b. Clear? Now what is my objective in this question? My objective is clear, is to calculate here value of m. Value of m, this is given by tau upon b sine of theta. Clear? Now what is value of tau? So it is given here 4.5 into 10 to the power minus 2 joule. So 4.5 into 10 to the power minus 2 joule divide by value of b. Value of b is given 0.25 Tesla and multiplied with sine of 30. Clear? Sine of 30. Clear? So from here we can say value of m is 4.5 into 10 to the power minus 2 divided by, we can say this is 1 by 4. Clear? And multiply 1 by 2. So we can say this one is 8. 8 will go to the numerator. So 8 into, I can say this is 9 by 2 multiply 10 to the power minus 2. Clear? And here we will find unit. This is joule per Tesla. Clear? From here you can see this one is 4. So directly we can say this is 36 into 10 to the power minus 2 joule per Tesla. Clear? So this is the value of magnetic dipole moment. Clear? So this is all about this question. Now we are going to discuss question number 5.4, and in this question it is given to you a short bar magnet of magnetic moment small m equal to 0.32 joule per Tesla is placed in a uniform magnetic field of value, this is 0.15 Tesla. If the bar is free to rotate in a plane of field, okay fine, which orientation could correspond to its stable and unstable equilibrium. Clear? So whenever you will find this type of term, stable equilibrium or unstable equilibrium, it means this question is related to potential energy of this dipole. Clear? Or we can say potential energy of this short dipole. Clear? So first let us try to understand concept of this question. After that we will find here answer of part number A, stable and unstable equilibrium. Clear? And we also calculate here potential energy in each case. Clear? So now consider. Let's suppose I am assuming this is uniform magnetic field, and uniform magnetic field is in this direction. Clear? let's suppose I am taking here a short, we can say, let's suppose this is a short dipole, we can say this is short, we can say bar magnet, clear, and I am assuming this is north pole and this one is south pole, clear. Now definitely you know, if we are talking about this is the line of axis, or we can say this is magnetic axis, clear. So magnetic field and magnetic axis is making some angle. So let's suppose I am saying this is a direction of magnetic moment, you can say, and this angle is theta, clear. So now we know potential energy expression for potential energy, this is given by, definitely you know what is the derivation, you know very well, but I am directly writing here expression. So expression of potential energy, this is given by mb, I can say this is cos theta 2 minus cos of theta 1. Now listen carefully, this theta 1 I am taking, this is equal to theta, clear, but I am actually taking here reference, this is perpendicular to magnetic field, clear. It means you can say if I am talking about theta 2, so this theta 2 is 90. Now you can say, sir, why you are taking reference at 90 degree? Because let's suppose if I am bringing north pole from infinity to a certain point and we are bringing south pole from that infinity to a certain point. Let's suppose we are assuming, so if we total calculate here time, so total time taken, let's suppose if we are talking about this north pole, definitely we have to apply here some force against the repulsive forces, clear, and here we have to apply some force against attractive forces, so that both poles it may move with the constant velocity, yes or no. It means we can say if we are talking about net work done we always find at a position perpendicular to this magnetic field always 0, clear. It means we can see here, that's why we are taking this reference at 90 degree, clear. So now if I put here this value, I can write like this, potential energy expression, this is given by mb cos 90 minus, I can say this is cos theta, clear. Now we know value of cos 90 0, so we can write like this, potential energy expression, this one is given by mb cos of theta, clear to you. Or you can also write like this, potential energy, this is given by minus times of m dot b, clear. Now if I talk about stable equilibrium, clear, I am now talking about part number A. So for stable equilibrium, the potential energy should be minimum, yes or no. So if I am talking about stable equilibrium, I can say expression of potential energy, this should be minimum, clear. So when expression of potential energy is minimum, I can say this is possible only when theta equal to 0, clear. We can say when theta equal to 0, it means what is actually diagram, how can we draw here the diagram or position of a stable equilibrium. I can say, let's suppose this is a direction of magnetic field, clear, and I am taking here this short dipole like this, clear. Here we have a north and this one is south, clear, and definitely we can say direction of magnetic moment is also in the same direction, that is m, clear. At that time you will find there is a 0 angle between magnetic dipole moment and magnetic field, clear to you. So from here we can write here expression of potential energy, and this potential energy is minimum, and I can say this is mb cos of 0, clear. Value of cos 0 we have 1, so minimum potential energy we can write like this, this is minus times of mb, clear. Now you can put here value of m and b, you can calculate value of potential energy, clear. So now concentrate. Yes. Now concentrate. So if I write here all the values, potential energy minimum, this one is given by minus m. M is given to you, yes, 0.32, and it is multiplied with, I can say b. B is what? Magnetic field. Magnetic field value we have 0.15, clear. From here we can write like this, this is 32 by 100 and multiplied with we can say 15 divided by 100, clear. So we can say if you multiply, this is 0, we have 3, and we can say 48 divide by 10 to the power 4, clear. From here you can say this is 10 to the power 3, or you can also write like this is minus 4.8 into 10 to the power minus 2, and we can say this is joule, clear. So I can say minus 4.8 into 10 to the power minus 2 joule potential energy we are getting, and this is a condition of stable equilibrium, clear. So if somebody asks to you what is a condition of stable equilibrium, so when this short dipole, when bar magnet is aligned like this, that the angle between magnetic moment and the magnetic field is 0, this is a position of stable equilibrium. Now why we are saying this is stable equilibrium? So let's suppose if you disturb this bar magnet from this position to this position, at that time you can say actually you are disturbing in anti-clockwise direction, but we can say the restoring torque is acting in clockwise direction, and it will always try to restore this position, clear. That's why we are saying this is stable equilibrium, clear to you. Now if I talk about, listen carefully, now if I talk about we can say if we talk about position of unstable equilibrium, clear. If I am talking about unstable equilibrium, now you know very well potential energy expression, this is given by minus mb cos of theta, clear, minus mb cos of theta. So now let's suppose situation is like this. I am saying here this is a uniform magnetic field in this direction, clear, and I am taking here, let's suppose this is a bar magnet, we have here this is north and this one is south, clear, and I am saying here this is a value of m, clear, this is a direction of magnetic field. So actually what is angle between m and b here? That is 180 degree, yes or no? So from here we can say, we can write like this, potential energy, here you will find maximum potential energy, and this is equal to minus mb cos of, I can say this is 180 degree, clear. And you can also say this is a condition of unstable equilibrium. Now you can say, sir, why this is unstable equilibrium? So let us try to understand. Let's suppose I am taking this is a b, clear, and let's suppose if I draw here, this is bar magnet. Let's suppose this is bar magnet. I am saying this one is north, this one is south, clear. Now let's suppose you disturb this bar magnet in a anti-clockwise direction like this, clear, and now this bar magnet is placed in a magnetic field. Now you can say, sir, force is acting now on a north pole in this direction, and for the south pole this is acting in this direction, clear. So actually you displace this bar magnet in anti-clockwise direction, and force due to this uniform magnetic field, this is also in an anti-clockwise direction. So as you leave this bar magnet, at the time it will never come to its original position. Actually where it is going actually, it is try to attain the position of stable equilibrium, clear to you. So from here we can say, we can write like this, this is given by minus mb, and we can say this is minus 1, clear. So from here we can write like this, this is equal to plus mb, clear. So I can say maximum potential energy, this one is given by we can say plus mb, clear. So one question is very popular, yes, definitely this question is now completed, but one question is very important. Let's suppose if we want to move this dipole from condition of stable equilibrium to unstable equilibrium, what I am saying to you, let's suppose if I want to change position of this dipole from stable equilibrium to unstable equilibrium, what is the total amount of external work is to be done, clear. So now we can write like this, net work done, we can say this is equal to change in potential energy, we can say u final minus u initial, we can say this is mb minus mb, clear. So from here you can say this is plus twice of mb, and this is, my dear student, very important question, clear. So total we have to provide here twice of mb work, clear to you. Now you can put here all the values, that is plus mb we are writing here. So value of m, this is given to you 0.32, and multiply we can say this is 0.15, clear. So definitely you will get again same value, but we are getting this value in positive. So 4.8 into 10 to the power minus 2 Tesla, Clear to you? So this is all about this question. Now student, we are going to discuss question number 5.5, and in this question it is given to you a closely wound solenoid of 800 turns and area of cross section carries a current of something. Clear? It means what are the parameters are given to you? Number of turns. I am saying this is capital N and this value we have 800 turns. Clear? Area of cross section. Area of cross section is given to you 2.5 into 10 to the power minus 4. Clear? And it is also given current that is flowing in this solenoid, that is 3 ampere. Clear? So first we have to find here what is associated magnetic moment. So magnetic moment, that is actually given by I multiply A, but this is related to one current carrying loop. Clear? But let's suppose we have total n number of loops, then we can say this is equal to n times of IA. Clear? So number of turns is given to you, this is 800 multiply current is given to you 3 ampere. Clear? And what about cross section area? So we can say this is 2.5 into 10 to the power minus 4. Clear? So from here we can write like this. This is 7.5 multiply, we can say 800 into 10 to the power minus 4, and unit you will get, that is joule per Tesla. Clear? So if you multiply here, let's suppose we can write like this. This is 10, this one and this one cancelled out. Clear? From here you can see 8 multiply 5, we have 44. So 4 here, 56, we can say 600. Clear? And multiplied with 10 to the power minus 3 joule per Tesla. Clear? So from here we can write like this, value of magnetic moment, this one is given by 600 divided by 1000. Clear? And this is equal to 0.6. Clear? 0.6, I can say this is joule per Tesla. Clear to everyone? So this is value of magnetic moment. Now one more question is asking to you, explain the sense in which solenoid act like a bar magnet. Clear? So let's suppose I am saying, let's suppose this is denoting as a solenoid. Clear? And let's suppose current that is flowing in this solenoid. Clear? Now you know very well, whenever a current is flowing in a solenoid, and if you are talking about ideal solenoid, definitely magnetic field we will find that is along the axis of this solenoid. Clear? And definitely you should know that what is value of B. This is given by mu naught Ni. Clear? And N is what? Number of turns per unit length. Very, very important. Generally student commit a mistake here. They write here number of turns. This is not a number of turns. This is number of turns per unit length. Clear? So let's suppose I am taking here total number of turns, that is capital N, and length I am taking, this is L. Then you can write like this. This is equal to mu naught capital N divided by L multiply I. Clear? So now we have to compare how the magnetic field produced due to solenoid, it is resemble as a bar magnet. Clear? So first if I draw here magnetic field lines, so let's suppose magnetic field lines is actually like this. If you draw here pattern, you will find magnetic field lines like this. Clear? It means we can see here, you can see, if let's suppose I am assuming this one is north pole, this one is south pole. Clear? So magnetic field lines that is emerging out from a north pole and it is ending to a south pole. Clear? And if I am talking about inside this solenoid, this magnetic field lines is going from south to north. Clear to everyone? So actually this is just like this resemble just like a bar magnet magnetic field lines. Yes or no? So we can say you can assume magnetic field due to solenoid, it is just as a magnetic field due to bar magnet. Clear? So you can say you can just compare same. Clear? So this is all about this question. Now we are going to discuss question number 5.6, and in this question it is given to you, if the solenoid in exercise 5.5 is free to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied. Clear? What is magnitude of torque on the solenoid when it axis makes an angle 30 degree with the direction of applied magnetic field? Clear? So again a very simple question we have to apply here a formula for torque, and torque is given by this is mb sine of theta. Clear to everyone? Yes. So we can write here torque, this is equal to mb sine theta. My objective in this question is to calculate this one. So I can see value of m. Value of m we can take from previous question, and we can say this value we are getting, this is 0.6 joule per Tesla. Clear? Value of magnetic field, this is given 0.25. Clear? And value we can say angle between magnetic moment and magnetic field, this is given to you 30 degree. Clear? So from here we can write like this, this is 6 by 10 multiply, I can say this is 1 by 4 into sine of 30. Clear? From here you can write like this, this is 6 by 10 multiply 1 by 4 into 1 by 2. Clear? We can say this one we have 3. Clear? So from here you can say this is 0.75 divided by 10, and we can say this is 0.075 Newton meter. Clear? So like this you can calculate total torque that is acting on that solenoid. Actually this is just like, let's suppose you have a bar magnet, let's suppose you connect a thread and you held vertically that bar magnet. You know that bar magnet is actually align itself in a north-south direction. Let's suppose if you apply some external torque, and due to that external torque that bar magnet is tilted. Clear? At the time a restoring force will act, and that actually restoring force, actually we can say a torque will act, and it will again try to align that bar magnet in the same north-south direction. Clear? So same you can assume here, this is a torque that is acting on that solenoid, and that again bring that solenoid in a initial position. Clear? So this is all about this question. Now student, we are going to discuss question number 5.7, and in this question it is given to you a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. Clear? Now part number A, what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? Number 1, normal to field direction, second one opposite to field direction. Clear? So let us try to understand this question. Let's suppose I am taking initially magnetic field in this direction, and let's suppose I am taking this initial magnetic field, or you can say uniform magnetic field. Clear? Now let's suppose I am taking here, this is a bar magnet. Clear? This is bar magnet, and let's suppose this is north and this one is south. Clear? And now if I am talking about direction of magnetic moment, this is also in this direction. So we can say initial position we are taking, this is 0. Clear? Now what will happen when I turn this bar magnet perpendicular to this magnetic field? Definitely we can say at the time theta 2 becomes 90 degree. Yes or no? When we place this bar magnet perpendicular to this magnetic field, from this direction we have angle 90 degree. Clear? So now you know we can write here expression of potential energy. Potential energy we can write like this, mb cos of theta 2 minus cos of theta 1. Clear? So first let's suppose we want to turn this dipole from this side to perpendicular. So at that time I can write potential energy expression, this is given by mb, I can say this is cos of 90 minus I can say this is cos of 0. Clear? So value of cos 90 we have 0, and cos 0 equal to what? 1. Clear? So from here we can write like this, this is potential energy, this is given by minus mb. Yes or no? Cos 90 directly we can say this is 1. So what is amount of work done? So we can say total external work done, this is given by directly we can say minus times of change in potential energy. Clear? Or we can say this is equal to plus times of mb. Clear? Now value of magnetic moment, it is given to you 1.5 multiply what is value of b? B value is given, this is 0.22. Clear? So from here we can write like this, external work done. So W external, this one it is given by 15 divided by 10 and multiply 22 divided by 100. Clear? So if you multiply you can say we have 30, this is 330 divided by 1000, and from here we can say 0.330 and this value we have joule. Clear? So from here we can write like this, external work done, this external work done is this one. Clear? Now let's suppose we want to move this dipole opposite to the direction of magnetic field, then what will happen? Clear? So concentrate here. If I simplify this expression, I can see now situation changes. Now this theta 1, we can say this theta 1 is already 0, this theta 1 is 0, but what about theta 2? Clear? We can say this theta 2 now becomes 180 degree. Clear to everyone? So in situation number B, or we can say part number 2, whenever we are changing this dipole in opposite direction, this theta 2 becomes 180. So here we can write this is 180. Clear? What is value of cos 180? Minus 1 and minus 1, minus 2. We can write like this. This is plus times of twice of MB. Yes or no? Yes or no? This is minus 1 and minus 1. I can say this is minus of 2 MB. Clear? This one is minus times of 2 MB. Now we can write here external work done. This is equal to minus times of change in potential energy. I can see that is plus of twice of MB. Clear? It means we have to multiply here 2 also. Clear? So we can write like this. This is 2 multiply this one, 2 multiply this one. Clear? So final answer we are getting this is 0.66 joule. Clear? So we can say what is correct answer here? Correct answer we can say this is 0.660. 0.66 joule. Clear to everyone? Okay. Now what is torque acting on the magnet in case number 1st and case number 2? Clear? So we can easily calculate here. We can easily calculate value of torque that is acting. Clear? Now if we talk about situation number 1, in situation number 1 you can say torque, this is given by MB, I can say this is sin 90. Clear? So from here we can say this is equal to MB. Clear to you? And MB value we can say you can put here value of M, that is 1.5 multiply I can say 0.22. Clear? So 15 divided by 10 multiply 22 divided by 100. So from here we can say this is 30, we have 330 divided by 1000. Clear? So from here you can say this is 0.33 Newton meter. Clear? Clear to everyone? So this one is a torque, this is acting over the part number 1. Now what is torque acting in this one? Clear? So directly you can say yes, directly we can say here value of torque is given by MB sin of theta. Clear? Now when I am changing position of a dipole from angle 0 to 180, it means I am writing like this, value of torque equal to MB sin of 180. Yes or no? Angle is now 180. Now we know this is 0 Newton meter. So always keep in mind, whenever any dipole is situated either in a direction of magnetic field or in an opposite direction of magnetic field, you will always find net torque that is acting 0, but definitely we have to do some work if we are changing position of a dipole from stable equilibrium position to vertical or from stable equilibrium to unstable equilibrium. And clear, definitely you know total amount of work that is required, that is equal to plus times of 2 MB. Clear? Very very important question. So this is all about this question. Now student, we are going to discuss question number 5.8, and in this question it is given to you a closely wound solenoid of 2000 turn and area of cross section 1.6 into 10 to the power minus 4 meter square carrying a current of 4 ampere is suspended from its center, allowing it to turn in an horizontal plane. Clear? Always keep in mind, whenever we have a solenoid, definitely number of turns will be given to you. Clear? Current that is flowing is also given and area is also given. So can we calculate here value of magnetic field? Yes, that is equal to mu naught Ni. N is the number of turns per unit length. This is a standard terms that you should keep in your mind. Clear? Standard formula. But here what is our objective? Our objective here is to first calculate magnetic moment associated with solenoid. Clear? So how can we calculate? Actually we know formula of magnetic moment. This is given by NIA. N is what? Number of turns, I is a current and A is the area. So number of turns, I can say number of turns we have, this is 2000 multiply, I can say current that is equal to 4, and what about area? Area is given 1.6 into 10 to the power minus 4 meter square. Clear? So from here if you write here, we can write like this, 4 into we can say 16 into 100 into 10 to the power minus 4. Clear to you? This point remove, this 10 is cancelled out, 16 into 8, we can say 16 into 8 multiply 100 into 10 to the power minus 4. So from here you can write like this, we have this is 8, we have 4, so 128. So from here we can write like this is 128 into 10 to the power minus 2, clear, and this value we are getting in joule per Tesla, clear. So from here I can write like this is 1.28 joule per Tesla, clear to everyone. So this is all about part number A, magnetic moment, clear. What is force acting? Now always remember, whenever we place any current carrying wire in a magnetic field, clear, at that time we know, and definitely when the current is flowing, what about the force? Force acting, it will be 0. Why? Because this is a closed loop, clear. If you calculate here total force acting by a formula that F equal to BIL sin theta, clear. For every small element you will find net force that is always acting either inward or outward direction, it depends on a current condition, clear, and you will find always net force acting that is 0, clear. So always keep in mind net force you will find that is 0, clear. How this is possible? Let's suppose first I am taking here, let's suppose this is 1 turn, clear. For 1 turn, let's suppose current is flowing like this and magnetic field is like this, clear. So you can see if you use here right hand rule or left hand rule, whatever, so at that time let's suppose I am saying here the force is acting in this direction, here force will act in this direction, force will act in this direction like this. So now we can say one force is actually cancelled by another force, clear. So directly we can say net force is 0, clear. But what about net torque, clear. Net torque we can say, because it is an objective, here in this question we have to calculate torque if uniform horizontal magnetic field it is given to you and it is set up at an angle of 30 degree with axis. So I can write like this is MB sine of theta, clear. Value of M, magnetic moment, this is 1.28, value of magnetic field value is given 7.5 into 10 to the power minus 2 and multiplied with I can say sine 30, clear to everyone, sine 30. So sine 30 means we can say this is 1 by 2 and this one is 0.64. So 0.64, clear, multiply 7.5 into 10 to the power minus 2, I can say this is Newton meter, clear. Now we can simplify this expression. Yes, now we can simplify value of torque, clear. So we can write like this is 64 by 100 and multiplied with, because this is 7.5, you can write like this, if you multiply it with 10 and divide with 10, clear. If you divide with 10 you can say this is 0.75, you can say this is 3 by 4 and I can say this is 10 to the power minus 1, yes or no. I am multiplying with 10, dividing with 10. So if I divide this is 0.75 multiplied with, so it becomes minus 1, clear. So Newton meter. So from here you can say this one is what, 16, clear. So we can say this is 48 multiply 10 to the power minus 3, clear. 48 into 10 to the power minus 3 Newton meter, clear. So this is value of torque that is acting on this solenoid, clear. So this is all about this question, but actually here you should always keep in mind that here we writing here this M, and in M we already included here number of turns, clear. So do not multiply it with again with number of turns, clear. So this is all about this question. We are going to discuss now question number 5.9, and in this question it is given to you a circular coil of 16 turns and radius 10 centimeter carrying a current of 0.75 ampere. So first I am writing here, we have circular coil having number of turns 16, number of turns it is given to you 16, radius this one it is given 10 centimeter, clear. So we can convert into meter, so 10 to the power minus 1 meter, carrying a current of 0.75 ampere. I am writing here this is 3 by 4 ampere, clear. So it will be easy for calculation, and it rests with its plane normal to an external field of magnitude. So magnetic field value is given 5 into 10 to the power minus 2 Tesla, clear. Now this coil is free to turn about an axis in its plane perpendicular to field direction. Clear? It means we can say initial this coil is in stable equilibrium. Fine. And it is also given when coil is slightly turned and released, it oscillates about its stable equilibrium with the frequency of 2 per second. It means do you know whenever we turn any dipole means if we are talking about short magnet, if we turn about from this stable equilibrium, we always find the expression of a time period, and we can also calculate time frequency. So we can see frequency is given by 1 upon 2 pi or under root of mb by I. Clear to you? This formula is clear? 1 upon 2 pi under root of mb by I. So from here, can we calculate value of moment of inertia? Yes, because our objective in this question is to calculate inertia. So now we can say value of I, this is given by, first I am doing square, so this is mb divided by 4 pi square and f square. Clear to you? Now one more thing is given here, value of frequency is given 2 per second. Clear? So 2 per second. Clear? 2 per second means 2 revolution per second. Now first we will calculate here value of m. So we can write like this: m, this is magnetic moment, it is given by NIA. Clear? And number of turns, this is 16, current that is flowing here, this is 3 by 4 and multiply with area. Now because this is circular coil, so we can write like this: this is pi r square, pi into 10 to the power minus 1 whole square. Clear? So we can say this one is 4, so we can write like this: magnetic moment, this one is given by 4 multiply 3, this is 12 pi into 10 to the power minus 2. Clear? So this is value this is the value of magnetic dipole moment. Clear? 12 multiply pi multiply 10 to the power minus 2, and this is joule per Tesla. Clear to you? So now from here we can write what is moment of inertia. So now we can put here this value. Always keep in mind this I is the current. Clear? And this I is moment of inertia. I can write like this so that you will never confuse. This is I dash. Clear? So actually we are calculating here I dash. I dash is given by 12 pi into 10 to the power minus 2. This is value of magnetic moment. Clear? And now value of B, this is given 5 into 10 to the power minus 2. Clear? It is divided by 4 pi square. So I can say 4 into pi square I am approximately taking, that is 10. Clear? And f square means we can say this is 2, so 2 multiply 2. Clear? Now we have to just simplify it. So from here we can say this one is 3. Clear? So this is equal to 3 pi into 5 into 10 to the power minus 4 divided by, I can say 4 multiply 10. Clear? So we can say this one is 2. Clear? So from here you can write like this: this is 3 pi by 8 and multiply 3 pi by 8 multiply 10 to the power minus 4, and this is in unit kilogram meter square. Clear? Because we know moment of inertia is having unit kilogram meter square. Clear? So now from here you can see if you calculate, you can put here value of we can say pi, and you can get final answer of moment of inertia. Clear? So I dash value we can say this is 3 into 3.14 divided by 8 and multiplied with 10 to the power minus 4. Clear? So from here we can see this is what 12, we have 4, and we can see this one is 9 divided by 8 into 10 to the power minus 4. Clear? From here we can write like this: this is 1 point. Clear? 1 point, approximately I am saying this is 1.2 into 10 to the power minus 4 kilogram meter square. Clear? So like this we can calculate here value of moment of inertia. So now student, we are going to discuss question number 5.10, and in this question it is given to you: a magnetic needle free to rotate in a vertical plane parallel to magnetic meridian has its north tip pointing down at 22 degree with the horizontal. Clear? So definitely you know in earth, on this we can say for the earth we have two terms, geographical north and geographical south. We have one more term, that is magnetic north and magnetic south. So we can say the plane that is passing through magnetic north and magnetic south, that we can say that is magnetic meridian. So let's suppose we have a needle, let's suppose that is a, we can say, dip needle. So this is a special type of needle that can deflect in a vertical direction or in a vertical plane. Clear? So in this question it is given to you a magnetic needle free to rotate in a vertical plane parallel to magnetic meridian. Clear? Has its north tip pointing at 22 degree with horizontal. Clear? So let's suppose if I draw here one diagram. Let's suppose I am saying this is horizontal component of earth magnetic field. Clear? Now it is given in this question, this value we have 22 degree. Actually this is angle of dip. Clear? Angle of dip is the angle that is made with net magnetic field, with angle made between the net magnetic field and horizontal component of earth magnetic field. Clear? So now we can see, let's suppose this is B and we know this is BB. This is vertical component of magnetic field. Clear? So it is also given in this question, we have horizontal component of earth magnetic field, that is 0.35 Gauss. Clear? So from here can we calculate value of net magnetic field? Yes. From here we can write like this, cos of del. Cos of del, this is given by BH upon B. Clear? From here we can write like this, value of B, this is given by BH upon cos of del. Clear? Value of BH we have 0.35 divided by, I can say, cos of 22. Clear? Now what is value of cos 22? Clear? Cos 22, now we don't know exactly what is value of cos 22, because we know for a specific angle like 0, 30, 45, 60, 90. Clear? Sometimes we can also calculate like we can say, let's suppose if I am talking about 75. Clear? Let's suppose I am talking about 15. So we can also calculate that of angle. But what about cos 22? So whenever this type of calculation will come in any question, definitely value of cos 22 will be provided to you. Clear? So here I am providing this value, this is equal to 0.92. Clear? So we can say this value is 0.92. Clear to everyone? So from here we can write like this, this is 35 by 92. Clear to you? Yes or no? And we can see if you remove, let's suppose I am writing here this is decimal, I can say this is multiplied with 100 Gauss. Clear? So from here you can write like this, 0.35 multiply 100 divided by 92 Gauss. Now we can say 92 divided by 92, that is what? We can say directly we can say that is 1 plus. So can we also write like this, 0.35, this is 1 plus 8 by 92. Clear? Now we can say this 8 is what? This is not a 10% of this one. So we can say this is below 10%. Yes or no? So we can say this is 0.1. So let's suppose for an approximation I am taking this value is 0.1. Clear? So we can write like this, 0.35 multiply 0. We can say 1.1. Clear? We can say this is 1.1. So if you multiply 0.35 with 1.1, you will get here answer. So correct answer we are getting, this value is near about 0. We can say this is 38 Gauss. Clear to you? So like this we can calculate value of net magnetic field. Clear? So this is all about this question. Now student, we are going to discuss question number 5.11, and in this question it is given to you, at a certain location in Africa, a compass points 12 degree west of geographic north. Clear? So let's suppose if I am drawing here, let's suppose this is earth. Let's suppose this is earth. Clear? I am saying this is geographical north. Clear? And let's suppose this is geographical south. Geographical south. Clear? It is given in this question here, a compass points 12 degree west of geographic north. Clear? So let's suppose this is line, just a minute. Yes. So let's suppose I am saying this is a line like this, and we can say actually this angle is given to you, that is 12 degree. So actually this 12 degree is what? This is magnetic declination. Yes or no? Because let's suppose we are taking a plane that is passing through geographical north and geographical south, that is geographical meridian. clear. And definitely we know here if we have this is geographical north, clear. So definitely if we are talking about the earth magnetic field, clear. So earth magnetic field, definitely we can say here if we are assuming a bar magnet, in this side we have a south pole and definitely here we have a north pole, clear. So let's suppose if you suspend any bar magnet, so that bar magnet is having north in this direction. It means we can see if you draw here, let's suppose this is bar magnet. So for this bar magnet I am having this one is north and this one is south, clear. That's why we can say this is known as magnetic north and we can say this is magnetic south. Yes or no? But actually if we are talking about bar magnet, this bar magnet is having north this side and south this side. Clear to you? Clear? Actually we have two bar magnet. Listen carefully. At the center of earth we are assuming bar magnet is at the center of earth, clear. And we are also hanging here a bar magnet by a thread and we are getting this direction, clear. So now in this question it is given to you angle, we can say declination angle, it is given to you, that is 12 degree, okay, fine. So we can say alpha, value of alpha, that is given 12 degree, clear, okay. Now it is also given the north tip of magnetic needle of a deep circle placed in a plane of magnetic meridian point 60 degree above horizontal. So actually the situation is like this. Let's suppose I am assuming this is horizontal component of magnetic field. I am saying this value we have B, clear, and this angle is providing to you, that is 60 degree, clear. Now my question is here, the horizontal component is also given. It means value of BH is given 0.16 Gauss, clear. Now we have to specify direction and magnitude of earth magnetic field at this location. Now listen very carefully. First of all, you can assume what is the direction of horizontal component of magnetic field. So we can say horizontal component of magnetic field, this is along this magnetic meridian, clear. And we can say it is given here net magnetic field is at a certain angle with this surface, clear. Or you can assume that, let's suppose horizontal component of magnetic field lie in this screen and this resultant magnetic field is making some angle with this screen, clear. So this is just like that. So first, can we calculate here value of capital B? Yes. So I can write like this, value of cos 60, value of cos 60, this is given by BH over B, clear. So now I can write like this, B, this is given by BH cos of 60, clear. Now horizontal component it is given to you, we can say horizontal component, so that is 0.16, clear. So 0.16 divided by, I can say 1 by 2, clear. From here I can write like this, this is 0.32 Gauss, clear. So value of capital B, this is given by 0.32, clear. So finally we can see net magnetic field is having magnitude 0.32 Gauss and it is making an angle 60 degree with horizontal component of magnetic field, clear. So this is all about this question, clear to everyone. Now dear student, we are going to discuss question number 5.12 and in this question it is given to you a short bar magnet has a magnetic moment of 0.48 Joule per Tesla, okay. Give the direction and magnitude of magnetic field produced by the magnet at a distance of 10 cm from center of a magnet on the axis and on the equatorial lines, clear. So now concentrate on a screen. First I am going to discuss part number A, and in this part it is given, let's suppose we are taking a short bar. So let's suppose this is a short bar. I am saying this is, let's suppose this is north and this one is south, clear. Let's suppose I am taking this is north and this one is south. Let's suppose I am taking here, this is an axial point. Let's suppose I am taking this side. So let's suppose this is axial point and it is given here distance from center of a magnet, this value we have 10 cm, clear. So can we find here value of magnetic field at point P? Yes or no? Yes. We can write here value of magnetic field at point P. So what is formula? You know, for a short dipole, I can say this is given by mu naught upon 4 pi multiply twice m over r cube, Clear? Now value of mu naught. Mu naught is what? This is permeability. This is a permeability of free space. Clear? And value of mu naught, this is we know 4 pi into 10 to the power minus 7 divided by, I can say that is 4 pi multiply 2 multiply value of small m. This one we have 0.48. Clear? Divided by r cube. Clear? R cube means we can say this is 10 centimeter. So I can write like this, 10 into 10 to the power minus 2 whole cube. Clear? So from here I can write like this. This is equal to 10 to the power minus 7 multiply 2 multiply 0.48 divided by 10 to the power minus 1. I can say this is 10 to the power minus 3. Clear? So now from here I can write like this. This is 10 to the power minus 4. Clear? So now we can say here we have 6 and we have 1. So 8 and 9. So 0.96 into 10 to the power minus 4 Tesla. Clear? So we can write like this. This is equal to 0.96 Gauss. Clear? So this is value of magnetic field. This is value of magnetic field at any axial position, and axial position is already given 10 centimeter. Clear? Now because magnetic field is a vector quantity, so what is direction of net magnetic field? Definitely we can say here direction of net magnetic field that you will find in the direction of magnetic moment. Clear? So direction of magnetic moment that is given in this direction. So you will always find value of net magnetic field is also in the same direction. Clear to you? Yes or no? Yes. Now we can say, can we calculate here part number B? Yes. So listen very carefully. Now from here we can see, if I am talking about part number B, so in part number B we are talking about equatorial position. Equatorial position means what? Let's suppose I am taking here, this is short magnet. Clear? And let's suppose this is north, this one is south. Clear? I am taking one position, this one. Let's suppose this is point P. Clear? And we are assuming, let's suppose this distance is twice L. So I am saying this distance we have, that is L. Clear? And this distance is given to you R equal to 10 centimeter. Clear? Now can we find here value of magnetic field? Yes, we know formula. So let's suppose now I am taking, this is BP and this is given by mu naught upon 4 pi. Okay, you know what is exact formula of magnetic field at any equatorial position? Yes, we can write like this. This is given by m divided by r cube. Clear? So from here we can write like this. This is equal to 10 to the power minus 7 multiply 10 to the power minus 7 multiply m. M is what? We can say 0.48. Clear? And it is divided by r cube. R cube means we can say distance is given to you 10 centimeter. So directly I can say this is 10 into 10 to the power minus 2 whole cube. Clear? Actually short dipole is given, short bar magnet is given to, that's why I am writing directly this formula. Clear? So from here we can see this is 10 to the power minus 7 and we can say 48 into 10 to the power minus 2 divided by, this is 10 to the power minus 1. So I can say this is 10 to the power minus 3. This one and this one cancelled out. This is 10 to the power minus 1. Clear? So from here I can write like this. This is 48 into 10 to the power minus 6 and I can say this is Tesla. Clear? From here you can also write like this. This is 0.48 into 10 to the power minus 4 Tesla. Now 10 to the power minus 4 Tesla, we can write this is equal to 0.48 Gauss. Clear? So this is equal to 0.48 Gauss. Clear? So this is the answer of part number B. Now okay, can you tell me what is direction of magnetic field at this position? Yes. In this case we can say direction of magnetic field we will find that is from north to south. This is the direction of resultant magnetic field. Clear to everyone? You can see like this. Let's suppose if we are taking from here and here. So direction at point P, due to this north we can write like this. This is BN and from this we can say this is direction due to magnetic field of south. Clear? So net direction we will find that is from north to south direction. Clear? So this is all about this question.